Okay. Similarly, using similar argument, you can prove that if the norm of A is less than R, there is also epsilon positive such that the epsilon neighborhood of A has empty intersection with S. You can prove this. Geometrically, the point A is now here, and the norm of A is greater than R, so you can take epsilon to be, this epsilon can be taken to be the norm of A minus R. Then you can show that any x in this neighborhood of A, the distance of this x to the origin, that is the norm of x, will be greater than R. So this ball, this epsilon neighborhood will have empty intersection with S. So this result follows. Okay. Okay, we have studied interior point previously, and then we just study exterior point and boundary point. Of course, we have a boundary. So our next task will be describe open sets and closed set using the boundary. Okay, this is our theorem. S is open if and only if it has empty intersection with the boundary. Okay, so this is if and only if necessary and sufficient condition. So we need to prove this in two directions. For example, first we proved the only if part. So if suppose S is open, we want to prove that the intersection is empty set. So for we would suppose S is open. Then we want this is what we want. Okay, we prove this. So for any A in S, because S is open, there exists epsilon positive such that the epsilon neighborhood of A contains in S. Therefore, this epsilon neighborhood of A has empty intersection with the boundary of S. Right? This implies that A does not belong to the boundary of S. For a point to belongs to the boundary, you need to guarantee that for any epsilon positive, the epsilon neighborhood of this point contains a point in S and a point not in S. But for this point A from the open set S, we have proved that there exists epsilon positive such that the epsilon neighborhood of this point is contained in S. Of course, this epsilon neighborhood of A has a point in S, but this intersection is empty, implies that the epsilon neighborhood of A does not contain the point in the complement of S. So this A could not be boundary point. So this is why we declare A does not belong to the boundary of S. So this argument means that once a point belongs to S, it could not belong to the boundary of S. Therefore, the intersection of the boundary and the set S itself is empty. Okay, so we have proved this part. The other part, for the other part, we can argue similarly. That is, we know that the intersection is empty. We want to show that S is open. What we want is to show that S is open. Okay, how to do this? You want to prove that S is an open set, then for any A in S, you need to find an epsilon positive such that the epsilon neighborhood of A contained entirely in S. Okay? Because the intersection of S and the boundary of S is empty, so once A belongs to S, A could not belong to the boundary of S. Right? A is not a boundary point of S, which means there exists epsilon positive such that the epsilon neighborhood of A has empty intersection of S, which S, or the epsilon neighborhood has empty intersection with the complement of S. Okay, so these two cases, one of these two cases must happen, and this is guaranteed by the fact that A is not a boundary point. So we have such an epsilon. Okay, if for any epsilon, both of these two intersections are not empty, then A is a boundary point by the definition of boundary point. So since A is not a boundary point, we have this conclusion. So because A already in S, right? Because A is in S, A in S means that this could not happen because A belongs to S. And because A belongs to S, of course A also belongs to the epsilon neighborhood of A. Therefore A belongs to these two sets. So this intersection at least contain one point A. Okay, so this could not happen. Therefore this is the case that can happen. The only case that can happen. But this implies that the epsilon neighborhood of A is contained in S. So A is an integral point of S. So we have proved that every point in S is an integral point of S. So by definition, S is open. So the theorem is proved. Now we use the boundary to describe the closed set. We have just described the open set using boundary. A set is open if and only if it has an empty intersection which is boundary. Okay. How about closed set? Okay, this is the topic of our theorem. S is closed if and only if the boundary of S is contained in S. Okay, we prove this result. The proof is quite easy. First, this direction. If the boundary is contained in S, we show you that S is closed. Suppose the boundary is contained in S, but as I tell you when we introduce the concept of boundary, every set has the same boundary which is complement. The boundary of S is exactly the boundary of the complement. Okay, so we conclude that the boundary of the complement is the boundary of S, but the boundary of S is contained in S. So this implies that the boundary of the complement has empty intersection which S complement. By our previous theorem, this implies that the complement is open. Thus, S itself is closed. Okay, so this part of this theorem is proved. Here, S is open is obtained this result from our previous theorem. Okay, so this argument can be reversed. This argument can be reversed to give this part of the proof. So if S is closed, then the complement is open. Thus, the boundary of S, the boundary of the complement has empty intersection which the complement of S. So the boundary of S, which is exactly the boundary of the complement, will contain in S, because this boundary has empty intersection which the complement of S, right? So it has to contain in S. Therefore, this is proved. Thank you.